Okay, you can start. You know how the distribution of the problems is.
Yes. Are you going to just go through the problems now? All right. All right. This is going to be the SMT 2022 problem recap. We have selected some problems that we think are insightful or nice, and we are going to go over these. So I will be taking the first question. This one is from the algebra test, and it's number 4. So the question states, gives us 3 polynomials, and they give a bunch of roots. So the r's are going to be roots of this first polynomial here. S's are going to be here, and then t's here. And the question asks, compute the value of this sum of these smaller sums. So just to make sure we all understand what this means, the first sum is going to be interpreted as R1, S1, R2, R1, S2, and pretty much every combination of I and J that fit these criteria, we can write R that, S that. So for example, we could have like R10, S20, or really anything that we want, as long as the two indices I and J are between 1 and 2022 inclusive. So we can write it so that the last term is R2022, S2022. And the same applies for each of these sums. The goal is to get this value given that these are roots of these 3 polynomials. And to do this problem, we can split each summation as follows. You see a summation of products. We can actually write this as a product of summations. What I mean by that is, let's just fix the I for now. And let's look at the SJs. So what happens is we have R1 and then all possible J's. So S1, right? We have S2, and pretty much we factor out the R1 so that the inside is going to be S1 plus S2 all the way to S2022. And we can do the same for each of the RIs. So R2 is going to have S1 all the way to S2022. And you notice that all the parentheses are actually going to be the same because, the choices of the J's does not depend on the choices of the I's. And so you get this big summation of R1, S1 plus S2, and so on to S2022, same with 2022. So then we can factor once again, we can factor out the sum of the S's. So we can write the summation that is common to all of them. And then let's see what's left. Well, it's just R1 plus R2 to R2022. And that's very nice because we know the sum of the roots of each of these polynomials. I mean, if we use Vieta's formulas, the sum of all of the r's, basically the roots of the first polynomial, must be 7. The sum of the roots here is 8, and the sum of the roots here is 9. So that means that if we consider the sum over here, this is just going to be, so the sum of the R1s is 7 times 8, 8 times 9, 9 times 7, and then we can calculate that real quick. 7 times 8 plus 8 times 9 plus 9 times 7, and that is 191. Yep.
Okay, so this was from the geometry round. It was also number 4. And here you have a triangle with this angle condition that angle A is equal to 135 degrees over 2. and BC is 15, which I'm just going to set that aside for now. It's just a scaling condition, so we don't need to worry about it yet. And we have the square, which is inscribed in the triangle, and point W is on AB, X is on AC, Y does not have to be on any side, and Z is on BC. And what we are given, other than the definition of the squares and stuff, is that triangle ZBW is similar to triangle ABC. So first we call this angle B and beta, and this angle gamma. Then we have beta plus gamma equals 180 minus 135 over 2, because the sum of the angles in a triangle is 135 over 2. And then, because ZBW is similar to ABC, this angle is equal to, for convenience, I'm going to define theta as 135 over 2 because it's just faster to write. Then A is theta and Z is also theta, and omega is gamma. Another thing we can extract from the similarity condition is the ratios of the side lengths. And from this, we know that BZ over BA is equal to ZW over AC and is equal to BW over BC. And we want to choose two of these ratios to focus on. We definitely want to focus on ZW as it involves the side length of the square. And we also, the only known side length we have is BC itself. So we probably want to use BC because it's a subsection of that line. And from this equation, we have that BZ is equal to, okay, so we can define AB as C, AC is B, and BC is A. Then we have BZ is equal to, and the side length of the square is S. Then BZ is equal to S times C over B. And this does not by itself tell us anything, so we should try to look for something more. And one thing about this problem is this angle condition, 135 over 2. And this looks like it might be a nice angle in terms of trigger just side lengths, but it's not really nice. Instead, a property of it is that 135 over 2 is 180 minus 45 over 2. So 2 times 135 over 2 plus 45 is equal to 180. And from here, we can notice that if we draw the line ZX, because this is going to be 45, angle XZC is theta. And then filling in, we have that ZXC is beta. And from here, we have that triangle ZXC is similar to triangle ABC. And then again, by the similarity ratios, we get that ZC is equal to, ZC is equal to B over C times ZX. And ZX is square root of 2S because it's the diagonal of the square. So we have this equation. And in relation, the relationship between VZ and ZC is that they add up to 15. And we can write out the formulas for these. And we get this. And now we remember that the problem asks us to maximize the value of S. So we want to minimize this. And the fact that the variables are flipped in the numerator and denominator suggests that we use AMGM. And that tells us that C over B plus B root 2 over C is greater than or equal to 2 times the 4th root of 2. And then we have that S is less than or equal to 15 over 2 times the 4th root of 2. So S squared is less than or equal to 225 over 2 over 4 root 2, which simplifies to 225 root 2 over 8. And to construct this, because this is just an upper bound yet, so far not yet an answer, we just need to find the AMG inequality case, which is when C over B is equal to B root 2 over C. Then we have C squared equals 2B squared, and we just choose the values needed, which can be found by applying law of cosines on triangle ABC with respect to the known angle. So this gives a construction for 225 root 2 over 8, so it is the answer. Are there any questions?
Okay, so next we'll go over the next question on the SMT geometry round, which is number 5. So we are given a quadrilateral with several side lengths, and we are asked to find the length of a certain segment. So we can start by drawing the quadrilateral ABCD, which should look something like this. And when we fill in the side lengths, we can notice that angle ABC is 90 degrees, and also angle ADC is 90 degrees by Pythagorean theorem. So we know that ABCD is cyclic. And from here we have we can use similar triangles. Let me draw in. So M is here and N is here. So we can now use similar triangles because we know that BAC, angle BAC is congruent to angle BDC. And we know that angle ABD is congruent to angle ACD. So we can mark in these angles, and then because these are vertical angles, we have that triangle ABN. ABN is similar to triangle CDN. And now all that remains is to find the length of BD, and then we can use similar triangles to finish off the problem. And then we can find the length of BD by noticing that the cosine of angle ABD is equal to the cosine of ACD, which is equal to 7 over 25. And then let's go down. So now by the law of cosines, we have that BD squared is equal, we have that AD squared is equal to 20 squared plus BD squared minus 2 times 20 times BD times, times the cosine of angle ABD. So we have 24 squared is equal to 20 squared plus BD squared minus, this is 280 over 25 times BD. And then we can solve this using the quadratic formula. And then what we notice is that BD is actually 20. And what that means is that ABD is isosceles. And so what we can, and now if we go back to the diagram, if we let AN equal X and BN equal Y, then NC is equal to 25 minus X, and BD is equal to 20 minus Y. So I'll put that there. However, by similar triangles, we can write that 25 minus X, which is the length of CN, is also equal to 7 over 20 times Y because of similar triangles on the length of BN. And similarly, 20 minus Y is equal to 7 over 20 minus X. 720 times X. And now this is just a matter of solving these two equations. And you can do this through elimination or substitution, but what we see at the end is that x is equal to 800 over 39. And so our desired length, which is mn, is equal to an, which is x, minus am. However, because m is the midpoint of AC, we know that m is also the center of this cyclic triangle ABCD, because ABC plus ADC is 180 degrees. So ABC so AC is the diameter of the circumcircle. And so in this case, MN is equal to 800 over 39 minus 25 over 2. And this gives our final answer of 625 over 78. Do you have any questions?
All right, then we'll move on to problem 4, which is number 5 from algebra. The question gives us that x, y, z is 10. X, y, and z are real numbers. Doesn't state if they're positive or negative. It asks for the maximum possible value of x cubed, y cubed, z cubed, minus 3x to the 4, minus 12y squared, minus 12z to the 4. And if we look at this expression, we already see an x, y, z in there. And we know since x, y, z equals 10, we can get this for free. It's simply 10 cubed. And that's 1,000. What remains is to look at what the rest of these numbers mean. Since it's asking for the maximum possible value of this, we want like 1,000 minus this stuff is greater than or equal to something. Or sorry, less than or equal to something, because we want the maximum value to be whatever is on the right here. So this has to be greater than or equal to the thing on the left. So we can look at this expression. This means that this number, this expression that I just boxed, is greater than or equal to that maximum, 1,000 minus that maximum. Let's just call this m. So our goal is to find this value here. So we're given x, y, z is 10. So it kind of suggests that we use AMGM again, because we're given a product and we want to minimize, in this case, a sum of 3 terms. But as it turns out, if we just try taking the mean here, 3x to the 4 plus 12y squared plus 12z to the 4, that's just this was boxed above. If we take that and take the mean, well, we're gonna end up with something sort of weird. I mean, in here, it's gonna be a cube roots of, our terms 3x to the 4, 12y squared. And the problem with this is that we don't exactly know what this term equals. I mean, like the polynomial term is gonna be x to the 4, y squared, z to the 4 times, some constant on the left. But the issue is that we have 4, 2, and 4, which does not convert easily from x, y, z, right? We can't directly find this value here. It still depends on x, y, and z, even though the value x, y, z is fixed. What we do want is for all of these powers to be the same. And in that case, we can just simply substitute x, y, z equals 10 into the expression and get our desired answer. So this is a classic trick. In order to get the degrees to equal, the issue here is the y squared. We can just separate the 12y squared into 2 terms so that the y squareds multiply into a y to the 4. In this case, it works out as follows. We just split it in half. So 3x to the 4 plus 6y squared plus another 6y squared plus 12z to the 4. And this over 3, or this over 4 now, because there are 4 terms, this is going to be, according to AMGM, it's greater than or equal to the 4th root of the product of these terms. So 3 times 6 times 6 times 12. And then you see that it's x to the 4, y to the 4, z to the 4, which I'll just write as x, y, z to the 4. And I mean, this is great because now we know x, y, z, this is simply 10. So now all that remains is to calculate this on the right. So we quickly do that. Well, it's the 4th root of, so each of these contains a power of 3, so we can just take out the 3's there. What we're left with is 2, there's another 2, and there's a 4, and then 10 to the 4. So this becomes 16. We can see that 16 is 2 to the 4. So this is simply 4th root of 2 to the 4, 3 to the 4, 10 to the 4, and that's 60. Because 2 times 3 times 10 is 60. So that means that this expression over 4 is greater than or equal to 60. So that same expression is going to be greater than or equal to 4 times 60, which is 240. And once we plug back into this on the right, on the left here, we see that it's going to be 1000 minus this value is 240. And this maximum is going to be 760. Just to make sure that we have a construction, AMGM equality only holds if all of the terms are equal. And we see that this is possible because if we get 3x to the 4 equals 6y squared equals 12z to the 4, we know that there is a solution. Like because, okay, first of all, the 6y squares are equal. So so that's guaranteed. And then we can just find x, y, and z, scale them up or whatever, slowly increase each of these until their product is 10. There's a more rigorous way to talk about this, but that's the basic idea. So we can guarantee a solution. And so 760 is indeed the maximum. See how we divided these into equal parts? If we divided this into, say, 3 and 9 y squared, this would not be guaranteed because these two terms can never be equal when y is positive. So that is why we have to split it into equal parts so that equality is guaranteed. Yep.
Okay, so for this problem, Frank uses result that says that for prime p, a to plus 1 to the p is congruent to a to the p plus 1. And this is because one way to prove this is to just expand this using the binomial theorem. And then all the coefficients except the ones for a to the p and 1 are multiples of p. But another way to prove this is that this is congruent to a plus 1 by Fermat's Little theorem, and this is also congruent to a by Fermat's Little theorem. Therefore, these two expressions are equivalent. And now we can see when it doesn't matter that 1011 is not prime. And first we can observe that the problem gives a big hint. It tells us that he is mistaken because 1011 is not prime. So that motivates us to factorize it as 1011 equals 3 times 337. Now we can consider the equations separately, mod 3 and mod 337. When we consider it mod 3, we want x plus 1 to the 1011 to be congruent to x to the 1011 plus 1. And as seen earlier by Fermat's Little theorem, this can be x plus 1 to the 3 to the 337 is congruent to x to the 3 to the 337 plus 1. So then x plus 1 to the 337 is congruent to x to the 337 plus 1. And also, we can continue this similarly. This becomes x plus 1 to 336 times x plus 1, which is just congruent to x plus 1 squared. Well, this becomes x times x to the 336 plus 1, which is x squared plus 1. And okay, these two expressions should always be equal in mod 3. And I made a mistake somewhere here, but it doesn't really matter because you can always just check this in every case. If we select x is 1 mod 3, we have 2 to the 1011. It's going to 1 to the 1011 plus 1. And 2 to the 1011 is indeed 2, which we would expect from this, because if we look at the powers of 2 mod 3, they alternate between 2, 1, 2, 1. This is for odd, and this is for even. And then we can use similar arguments for the other residues. So for x is congruent to 0 mods 3, we just have 1 is congruent to 1. And for x is 2 mod 3, we have 0 is congruent to 2 to the 1011 plus 1, which you again know is true because 2 to the 1011 is 2 mod 3. So then we don't need to worry about the mod 3 part of this. We only need to worry about the mod 337 part. And we can look at the condition again. It says x plus 1 to the 1011 is going to x to the 1011 plus 1. And now we can use the idea I mistakenly used in the mod 3 part and separate this into 337 and 3. And then Fermat's little theorem states that x to the p is congruent to x mod p for all x. So this is x plus 1 cubed is congruent to x cubed plus 1. And expanding the left-hand side of the binomial theorem, we get 3x squared plus 3 is congruent to 0. So in 3x squared plus 3x, so x times x plus 1 is a multiple of 337. So then we have that x is either -1 or 0 mods 337. And the problem tells us that 0 is less than x and x is less than 1011. Then we can just write out all the possibilities. We have 336 and 337, and 674 and 673, as well as 1010. These two sum to 1010, and these two sum to 1010. So the answer is 3030. Are there any questions?
Okay, so now we'll do geometry number 6 from the SMT competition. We are given that the incircle of some triangle with directed angle BAC equal to 30 degrees, and we are asked to find the ratio of some areas. So we can start by drawing a general diagram for this. Because we don't know what angle of ABC or angle of ACB are, we would just not consider them. And this gives us a hint that we don't need to really consider what the angles of the other two are, and that this expression right here will cancel out nicely regardless of the angles. So first we can draw in this, with this being 30 degrees. And then we have our incircle with center I. And then this is M, N, and P. And basically what the area of BPC and BPC and area of BMC, because they have the same base, we are basically asking for the ratio of this height to the height of the entire triangle, and similarly the height of this to the height of the entire triangle. So we can call these h1, h2, and h3. And we're looking for h1, h2 over h3 squared. And what we notice is that h1 over h3, which is equal to cp over ca. Now, why is this? Because c, if we call this point x, then cxp is similar to triangle CNA because they have the same angle here, and these are both 90. So what we have, and so if we draw the in radius to P, M, and N, we call this A, B, and C. These are all equal by the ice cream cone theorem. This is equal to C over A plus C, And similarly, H2 over H3 is equal to B over A plus B. And now we simply have to find what C over A plus C is and B over A plus B is. So if we look at triangle PIC, we notice that C is equal to the cosine of angle ACB over 2 times CI from this right triangle here. And then if we look at triangle AIC, which is this triangle here, we notice that A plus C is equal, and we use law of sines, of course. We see that A plus C is equal to CI times sine of 180 degrees minus A over 2 minus C over 2 divided by sine of 15, divided by the sine of 15 degrees. And we can repeat this process for H2 over H3. And then we find that B is equal to cosine of B over 2, angle AB, C over 2 times BI, and A plus B is equal to the sine of 180 degrees minus angle of angle of BAC over 2 minus angle of ACB over 2. And what we notice, time divided by sine of 15 degrees. And what we notice from the sine of 180 degrees minus angle of BAC over 2 minus angle of ACB over 2 is that if we use trigonomic manipulations, this becomes the cosine of angle ABC over 2. And we know this because sine of 180 minus angle BAC over 2 minus angle ACB over 2 is equal to the sine of angle BAC over 2 plus the angle of ACB over 2. And that's equal to 90, the sine of 90 minus angle of ABC over 2, which is just cosine of ABC over 2. So what we end up with is that B over A plus B is just sine of 15 degrees. And this is also equal to C over A plus C. So our desired answer is sine of 15 degrees squared. And we know that, and this is equal to the square root of 1 minus the cosine of 30 degrees over 2 squared. And this is equal to 1/2 minus root 3 over 4. So this is the general solution to this. But the reason why I chose this question is because if you have no idea how to solve this question under time scramble, especially in a competition like SMT, then how are you supposed to solve this problem? Well, the fact that they don't give you angles of ABC and ACB give you a big hint. And this kind of like pushes you to think that what if I just choose a specific triangle for this, then it would have to be the same answer, right? Because the angles don't matter. So for example, if we set the angle ACB to be 90 degrees, and this is 30, we have a 30, 60, 90 triangle. And we know the ratio of the lengths in a 30, 60, 90 triangle. This is 1, √3, and 2. And if we draw our in circle now, we see that this nicely, because this is R. So this is M. MC is just R. We have AC. So what we're looking for is MC over AC times PB over PB over AB, which we derive from up there. And now all that remains is to find R, or the radius of the in circle. And we know that the area of the triangle is equal to the semi-perimeter of the triangle times R. So in this case, √3 over 2 is equal to 3 plus √3 over 2 times R, or R is equal to √3 over 3 plus √3. Yeah. And so finally, MC over AC is R. So MC over AC times PB over AB is R divided by √3 times PB, which is equal to NB, which is equal to CB minus R. So this is 1 minus R divided by 2. And this is equal to √3 over 3 plus √3 times 3 over 3 plus √3 divided by 2 √3. And this once again gives us 1/2 minus √3 over 4. Are there any questions?
All right, great. Next question is from the discrete round. This is problem 5. We have a classroom. Let's draw it real quick. It has 5 rows of 6 seats. You can also think of this as 6 columns of 5 seats, which will be maybe more convenient in this case. Anyway, we have 30 students, all different heights, and we're asked how many students expected that are going to be shorter than at least one person in front of them. The question is, or the condition is, they can't notice that you're playing games if any student in front of you is taller. So let's say you're this one, then one of these two have to be taller than you, and then you can safely play games on your phone. So a general rule of thumb when we're dealing with expected value problems is, well, we're going to be using linearity of expectation. So what I'm saying is, if you have 2 events, X and Y, then the expected value of their sum is the sum of their expected values in most cases. In this case, it holds. So this is a commonly used property that will simplify doing this question, because normally we would have to go through all of the arrangements, find like the number for each one, take that sum. It's really cumbersome, and it isn't worth doing, and I don't think it's even possible doing in the 1 hour time limit. So instead we use linearity of expectation. How can we apply this fact to this question? Well, we can now, thanks to this fact, consider each student separately, find the expected value, pretty much the probability that they're able to play games, and then add up all of them, all 30 of these. But we can calculate them separately, so it makes makes finding this answer much easier. Let's first start with the very front row. Well, I mean, these people can never safely play games on their phone because there's no one in front of them. So we're gonna say expected number for the front row is gonna be 0 each, right? And we can see that it's very symmetric. So anyone in the second row has the same probability of being able to play games on their phone as each other. And same for the third, fourth, and fifth row. So we just need to calculate the probabilities for each one person in each row. So let's take someone in the second row now. This person can play games on their phone if and only if this person in front of them is taller than them. So we're asking probability that in a random arrangement that, let's call this guy B and the guy in front A. And I'll just say these are the heights. So I'm saying probability that A is taller. So I just put a greater sign there. But probability that A is greater than B, that's going to be our expected value for this specific student. So then we look at all possible arrangements and the heights that these two get. There's a little shortcut here, is that the actual heights of these two people don't really matter. What matters is which one gets which. So like another way of thinking of it is, let's pre-assign the heights. So let's say one is 10, the other is 15, but we don't know which one's which. And then we can assign these to A and B randomly. So that means either it's 10 and 15 like this, or it's 15 in front and 10 in the back. And this works for any pair of numbers. So you know that these numbers 10 and 15 don't actually matter. So in exactly 1/2 of our cases, the second student will be safe. So B will be safe. And in this case, it's this one, because 15 is greater than 10. And in this case, this will not work. Once again, these numbers 10 and 15 can be chosen arbitrarily. I mean, it can be any pair of numbers, but there are always two ways and exactly one of them works. So probability that A is greater than B is simply 1/2. So that consists our expected value for the second row. So each of these has a 1/2 probability, and therefore in half of the cases they will be able to play games on their phone. Moving on to the third row over here, probability, we want the probability that of these three people, so we'll now introduce C, that's either A or B, so one of these, one of A and B is greater than C. Once again, we can pre-assign the heights and then look at all of the permutations of these heights. I'll just use 1, 2, and 3 in this case. Actually, if you think about it, you can safely play games on your phone as long as you're not the tallest person in this set, right? If you're not the tallest person, then the tallest person is either this one or this one, right? Of these three people, if you're not the tallest, then the tallest person is in front of you, so you can play games. So we're just looking at probability that you're not the tallest. And of course, that is 1 minus the probability of being the tallest. And of course, since we're assigning them randomly, each person has the same probability of being the tallest. In this case, since there are 3 people, it is simply 1 minus 1/3. And that is 2/3. Great. So now we have that the probability for the third row is 2/3 each. And then we can similarly do the fourth row. Since there are 4 people, including you, in front of you, that means that there is a 1/4 chance that you're the tallest of the people in front of you, including you, and therefore a 3/4 chance that you're not the tallest in your column in front of you. So that's a 3/4 chance that you will be able to play games. And finally, for the fifth row, that is a 4/5 chance that you're not the tallest of all the people, including you, in front of you. So then, of course, now all that remains is to do this final linearity step, which is simply to take all the expected values. In this case, the expected values and the probabilities, well, they're the same. So we just have 6 times, because there's 6 people in each row, we'll just take the 6 out. 0, 1/2, 2/3, 3/4, and 4/5. And what remains is a quick calculation, and we get 163/10.
Okay, so the next problem was number 6 on the discrete round, and it asks for the number of sequences satisfying this property with the absolute values. And generally, these absolute value conditions are slightly annoying to deal with. So I think a good way to start this problem would be to first write out all possibilities for small k. So initially, the first element can only be 1, and the second element can also only be 1 by definition. From here, the third element can only be 2, the fourth element can be 3 or 1, the fifth element can be 5, 1, or 3, the sixth element can be 8, 2, 4, 4, or 2. And notice that these 4s and these 2s are different in terms of the sequences because the sequences before them are different. So when we count the number of sequences at any point, we're just counting the amount of last elements listed here. So the answer for k equals 1 would be 1, k equals 2 would also be 1, 1, 2, 3, and 5. We could continue once more, and the value would be 8. And this section looks a lot like the Fibonacci numbers. And a way to justify this would be to try to use the recursive property of the Fibonacci numbers, which is that is the sum of the 2 previous numbers. But still, it's a bit hard to figure out how to do that. So instead, we can look for a bit more in what we have found. And indeed, we can find something. From here, there are 2 numbers that are greater than the one before them, and 1 that is less. Here, there are 3 that are greater and 2 that are less. In general, if this is nk, then the amount of sequences which are greater seems to be nk minus 1, and less seems to be nk minus 2. And we can then try to justify this. So let's say there are so far nk minus 1 sequences, of which nk minus 2 have a and then b where b is greater than a, and nk minus 3 have a and then b where b is less than a. And for large enough values, we don't need to worry about when they're equal because then the difference would be 0, which is not a possible element. Now here, we claim that nk is equal to 2 nk minus 2 plus nk minus 3. And this does seem a bit different from the Fibonacci recursive relation we were used to, but this simplifies to it because this is nk minus 2 plus nk minus 2 plus nk minus 3. And this is just nk minus 1. And this can be justified because when we're considering the absolute value recursive property, we don't care about anything above 2 elements before. We only care about the prior 2 elements. If we have a and b with b is greater than a, then we can use a plus b or B minus A, because the difference can be either A or negative A. However, if B is less than A, then B minus A is negative. Therefore, if B is greater than A, there are two possibilities, while if B is less than A, there is only one possibility. So we have the desired recursive relation. And from here, we just want to compute this 17th Fibonacci number with the scales defined as F1 is 1 and F2 is also 1. And if we do computation, we end up with 1597. Are there any questions?
Okay, next we'll be going over number 7 of the geometry round. So we have ABC has side lengths of 20, 15, and 7. And we are asked to find the distance between the orthocenter and the end center of DEF. So because ABC is an obtuse triangle, we can check this because 49 plus 225 is less than 400. We know that the orthocenter, which we can denote as H, will lie outside of ABC. So in this case, we can draw something like this. Where this is H, and then these are all 90 degrees. And then what we notice is that the end center of DEF, I claim that the end center of DEF is actually just C. So how do we prove that this is the end center of DEF? Well, we can do this by looking at cyclic quadrilaterals. So for example, we know that ADEB is a cyclic quadrilateral because we have ADB equals AEB equals 90 degrees. And therefore, if we let angle ABD be X, then we also know that angle ADEA is also equal to X. And next, we can look at cyclic quadrilateral HAFE. So we first look at ADEB, and now we look at HAFE. And what we notice here is that if we consider angle AEF, AEF is equal to AHF. AHF. But AHF is congruent to angle 90 degrees minus angle of HAF, which is equal to 90 degrees minus 90 degrees minus ABD. So what we did here is AHF, this angle right here, I'll use a different color. This angle is 90 degrees minus this angle. So if this is Y, then this is 90 minus Y. But if we look at triangle ADB, then this is also equal to ABD. So what we found is that the angle of AEF is also X. And this means that AE is the angle bisector of triangle DEF, or that C is in fact the end center of triangle DEF, if we repeat this for all the other sides. So now we're just looking for the length of HC. We know we just need to find HF minus FC, and this is equal to HC. But we know that FC is equal to FC is equal to AC times the sine of BAC. And we know that HF is equal to AF times the tangent of HAF, but we don't know, in fact, we don't know the angle HAF. So what we need to do now is separate HAF into CAF and HAC. So if we do this, we can rewrite AF is equal to AC times the cosine of BAC. And then once we have AF, we can rewrite tangent of HAF as the cotangent of ABC. And this is from what we found earlier, because HAF is 90 degrees minus ABC, which is equal to ABD. And thus a tangent of HAF is cotangent of ABC. And now all that remains to do is find the values of ABC and BAC. But what it turns out that it's actually quite nice, because the values of cosine of BAC, if we do law of cosines, this is equal to 4/5. Cosine of BAC is 4/5. And then the sine of ABC is equal to 3/5. So the cotangent of ABC is equal to 24/7. Oh, sorry, this is BAC. Cotangent, so sine of ABC is equal to 7/25. Yeah. And then finally, what we're looking for is HF minus FC, which is equal to 7 times 4/5 times 24/7 minus 7 times 3/5, and this gives us a final answer of 15. Are there any questions?
All right, then we'll move on to discrete number 7 from this year's test. We're given a starting number n naught, the product of the first 25 primes. I'll just write that as P1, P2, all the way to P25. For now, the actual values of these primes is not very relevant, or let's just look at the process right now. So we're choosing a random divisor of n naught. This choice is taken with probability proportional to phi of n1. Now, let's quickly digest what we just read. Phi, this is the number of integers less than m, which are relatively prime to m. And if you haven't seen the closed form for phi, you should probably memorize it now. It's very important. Pretty much it says that if phi n is p 1 k1 p2 k2 pm km, where these are all powers k's, and then this tells us that it's going to be 1 minus 1 over p1, 1 minus 1 over p2, all the way to 1 minus 1 over pm of times n. Essentially, this is just this is like, you can derive it through, for example, principle of inclusion exclusion pi, or many other ways, but this is the formula that you should know and apply. So we'll just take this for now. We're saying that the divisor is picked with probability proportional to this phi. So luckily, the prime powers here are all 1, right? It's just p1, p2, all raised to the first power, which means that if we try to take phi of this, let's just take phi of the whole thing for now, just to see how this works. It's 1 minus 1 over p1, so on, 1 minus 1 over p25, and then times p1, p2, p3, all the way to p25. And this is, well, we can group these two because they're both P1 terms. If you multiply that out, it's just P1 minus P1 times 1 over P1, that's 1. And P2 minus 1, and so on. So I just lost connection. Give it 1 sec. Am I still connected to the call? I think I am. Essentially, it's just going to be a product of Pi minus 1. So, okay, I'm back. Great. So pretty much phi of this is going to be the product of the primes minus 1. And in general, any divisor of P1, P2 all the way to P25 is going to be like P something. So some subset of the primes, right? Multiplied together. And then the phi of that would be just all of those minus 1, right? And so on. So for example, if you picked 1, 2, and 3, then it would just be P1 minus 1, P2 minus 1, P3 minus 1. Now let's consider what this question is asking. Once we do this process, so picking N1 and then picking N2 from N1, in the same way we did N not to N1, what is the probability that N2 is 0 mod this scary number 2310? And it looks pretty random, but if you try factoring it, well, it's like 10 times 231. That 231 is divisible by 3. You can get 3 times 77. And that 77 divides into 7 and 11. So, and this is 2 times 5, of course. So this number is actually 2 times 3 times 5 times 7 times 11. Which is just the product of the first 5 primes. How convenient. All right. The choice of this phi function to do this proportionality is sort of weird. And we'll investigate why we chose that. For this problem, let's just consider the probability that N1 is divisible by 2. This seems like a more doable question, and this will be the key to finding the whole solution. Well, so we have the divisors of P1, P2 all the way to P25. Some of them are going to be divisible by 2. Some of them are not. We want to see how many are divisible by 2 and then weight it based on this phi function as it states in the question. So, so what we're going to see is since P1 is 2, right, and everything else is odd, then N1 has to contain P1, and then it doesn't really matter what other primes we pick. Any subsets, so subset of like 2, 3, 225. It doesn't really matter how many or which primes we pick. This can be any subset. And then let's take a look at the rest of the divisors. The divisors that are not divisible by 2. Well, then it's just going to be the same thing, except we just remove the P1. So some subset of the 2 all the way to 25 down here. And we can see how similar these are. I mean, one of these is just P1 times the other, right? So then this gives us a very nice pairing. For example, we can pair 1 with P1, say 3 with 3P1. And pretty much what we're doing is pairing each number in this bottom set with P1 times that same number. And we'll get a bunch of these pairs. And then now we can use the phi proportionality here. The reason why the phi function is so nice is that it's something we call multiplicative. So phi of A times B is phi of A times phi of B. And this is true for all A and B that are relatively prime. So A and B, if GCD if A and B is 1, then phi is multiplicative. And we can kind of see where this comes from, because at least in this case, if we divide any number, for example, 2 times 3 times 5 into, say, 2 times 3 and 5, then the product of the phis is just it's going to be 2 minus 1, 3 minus 1 for this right side. And for the left side is 2 minus 1, 3 minus 1. The right side is 5 minus 1. And of course, when we multiply these together, we simply get the phi of the whole thing. And this holds in general, like no matter how we split it, as long as the two factors are relatively prime, we can see that the product of the phis is simply the phi of the product. We can apply this here by doing, for example, okay, so the probability that we pick the 1 is proportional to phi of 1. And the probability that we pick the p1 is phi of p minus phi of p1. And we can see that phi of 1 is 1. Phi of p1 is p1 minus 1. So in the first pair, the top has a p minus 1 times greater chance of being picked as the bottom one, 1. And this holds in general, actually, because if we have A on the bottom and then P1A, since A does not contain a factor of P1 by definition, this is because P1 was already picked, so A has to be some combination of other primes. Well, you can see that phi of P1A, since P1 and A don't share any common prime factors, that means they're relatively prime, which means phi1 of P1A is just simply phi of P1 phi of A. And that writes as P1 minus 1 times phi of A. So this is always exactly P1 minus 1 times the bottom one. And since when we consider all the pairs together, that means that the probability that N1 is divisible by P1 is simply P1 minus 1. Like if we have P1 minus 1 and 1, then like the top, which is like, if we combine all the pairs, we can see that the top is P1 minus 1 times as likely to be picked as the bottom. So in general, the probability that this is divisible is P minus 1 over a total number of cases, which is 1 plus P1 minus 1, because it was 1 here, P1 minus 1. So success, failure, it's going to be success over total, which is the sum of these is P1. So it's just going to be P1 minus 1 over P1. And this is true for any prime that is contained. So any of the P1, P2, all the way to P25. When we plug it in for 2, we get that's 1 over 2. So the probability that N1 is divisible by 2 is 1/2. And this is regardless of our choice of the other prime factors. So what this tells us is that the probability that N1 is divisible by 2 is 1/2. And if we want this to be 0 mod 2, 3, 1, 0, that means it's divisible by each of 2, 3, 5, 7, 11. So pretty much we can draw a tree. Let's just draw this tree here. We start with P1, P2, P25. There's a 1/2 chance that this number will contain a 2, so contains P1. And there's a 1/2 chance that it doesn't contain P1. And here it is impossible for us to pick a factor that does not contain P1 and have N2, so the next number, divisible by that P1, because P1 was not originally in this number. So there's a 0 chance that we get a number divisible by P1 from this branch. But from this branch, when we have a P1, we still have a 1/2 chance of getting another P1. And this is the good one, because this is N2, right? This is the only case that works. If P1 contains it, and then after that, we still contain it with a 1/2 chance. So we can see that this is going to be the bad case, because we remove the P1. So N2 in this case does not contain P1, but in this case it does. So the probability that it keeps that P1 after 2 cycles is 1/2 times 1/2. That's 1/4. We can do a similar tree for each of the other 4 primes, right? 3, 5, 7, and 11, except this time P1 will just replace that with 3, and this is 3. So this becomes 3 minus 1 over 3, or 2/3. So we can draw the same graph or tree. There's a 2/3 chance of keeping it first round, 2/3 chance of keeping it again, for a chance of 4/9 of getting a number divisible by 3. We can repeat for the other 3 primes. This is 5. So 4/5 chance, 4/5 chance. This gives 16 over 25. Next is going to be 7, so 6/7. It's just going to be 6/7 squared. And the last one's going to be 10 over 11 squared. So it remains to calculate 1/2 squared, 2/3 squared, 4/5 squared, 6/7 squared, and 10/11 squared. And then we can do that, cancel some of these out. So this becomes 2, this 10 here, and you end up with the number, you get 256 over, I think it's 5209, let me check. 256 of 5929. And that is our answer. That bottom is just 77 squared, by the way, so that's how you do it.
So I'm thinking let's do 2 more and call it end there. Sounds good?
Yep.
In that case, can I skip to a different problem, or I'd rather
Yeah, you
proceed?
can skip to a different problem.
Okay, so this is one of the last problems on the guts round, and it was one of the hardest problems as well. So you have this equation for k, and you want to find all possible values of k. So first we can try to rearrange this equation by multiplying both sides by ab minus 1. This gives a squared minus k minus 1 ab plus b squared is equal to negative k. And first we can try to use a technique commonly found in quadratic expressions such as these, which is called Vieta jumping. So we can start with a solution x comma y. We can say this is the smallest solution for a certain k. And then we can consider this as a quadratic in either x or y. Let's say in x for now. Then we have x squared minus k minus 1 yx plus, actually no, r squared minus k minus 1 yr plus y squared plus k equals 0. This is the quadratic of which solutions along with y generate the same value k. And we already know x is one of these solutions. Therefore, the other solution, which we can call x prime, is k minus 1 y minus x by Vieta's formulas, specifically the sum of the roots. By definition, and by assumption, we have that x prime is at least x. So it tells us that k minus 1 y is at least 2x. And similarly, we can find that k minus 1x is greater than or equal to 2y. Adding these, we get that k is at least 3. We can very quickly just make sure that k equals 3 does not work, because we can. And this gives a squared minus 2ab plus b squared equals -3. This is a minus b squared, so it can never be negative. So therefore we have k is greater than 3. Now we can try to find an upper bound on k. We can start by reusing the same quadratic expression and making a quadratic in b. Then we have b squared minus k minus 1 ab plus a squared plus k is equal to 0. For convenience, we can define s as the discriminant, which is k minus 1a squared minus 4a squared plus k, and that simplifies to a squared times k squared minus 2k minus 3 minus 4k. Then the solutions for this are b equals positive k minus 1a plus or minus the square root of s divided by 2. But we also know that if we set a and b as a small solution, and because the equation is symmetric, we can assume that a is greater than or equal to b without loss of generality. Then we also know that k minus 1a is at least 2b, as found earlier in this part. Therefore, we must have that b is k minus 1a minus square root of s over 2. And now we can use the other condition we have found in b, which is that k minus 1b is greater than or equal to 2a. From here, it's a bit of expansion computation. So we can rearrange this as b is greater than or equal to b over 2 is greater than or equal to a over k minus 1. 2b is greater than or equal to 4a over k minus 1. Or we could just directly go to 2b times k minus 1 is greater than or equal to 4a. Now 2b is equal to k minus 1a minus root s. So then we have k minus 1 squared a minus k minus 1 root s is greater than or equal to 4a. And from here, we can try to rearrange this. So first we move the a terms to one side and the other terms to another side. And that gives that k squared minus 2k minus 3 times a is greater than or equal to k minus 1 root s. And we can square and expand this to get k squared minus 2k minus 3 squared a squared is greater than or equal to k minus 1 squared times a squared times k squared minus 2k minus 3 minus 4k. And we can expand this, and that gives, first we can rearrange move all the a squared terms to one side, and that gives us that a squared times k minus 1 squared, k squared minus 2k minus 3 minus k squared minus 2k minus 3 squared is less than or equal to k minus 1 squared times 4k. And the right-hand side simplifies to a squared times k squared minus 2k minus 3 times 4. Then we have that a squared times k squared minus 2k minus 3 is less than or equal to k minus 1 squared times k. And this still is not sufficient, so we can try to remember what k itself is. And it is this expression. We also have that a is greater than or equal to b. So now we can try to bound this. And especially this denominator is hard to deal with. From here, we can observe that if b is greater than 2, then ab minus 1 is less than or equal to 2a. I mean, it's greater than or equal to 2a. So then we also have that this is less than or equal to 3a, but 3a squared because a is greater than or equal to b. So that gives that k is less than or equal to 3/2 a. Then 2/3 k is less than or equal to a. And you can square both sides to get 4/9 k squared is less than or equal to a squared. Now we can substitute this value of a. And that gives 4/9 k squared is times k squared minus 2k minus 3 is less than or equal to k minus 1 squared times k. And if we expand this and rearrange, this will eventually simplify to 4k cubed minus 17k squared plus 6k minus 9 is less than or equal to 0. And the computation is a bit messy, so I'm not going to show it here. And from this, the leading coefficient of this is positive, so for large enough k, this is not going to work. And in fact, this tells us that k is less than 5. Because for all k greater than or equal to 5, the value will be positive. And we already have k is greater than 3. So that gives k as equals 4 as our only value. However, we have this crucial assumption that b is greater than 2. So now we have to consider what happens when b equals 2. Then we have that k is equal to a squared plus 2a plus 4 over 2a minus 1. From this, we have that 2a minus 1 divides a squared plus 2a plus 4. And this itself is a bit annoying to deal with, so instead we can split this into two cases. The first is where a is equal to 2x for some x, or in other words, a is even. And the second case is a equals 2x plus 1. And if a is equal to 2x, we have 4x minus 1 divides 4x squared plus 4x plus 4. And then we can use the fact that 4x minus 1 also divides 4x squared minus 4x. Minus x. So that tells us that 4x minus 1 divides 5x plus 4. And therefore 4x minus 1 also divides x plus 5 because we can subtract 4x minus 1 from 5x plus 4. And if a divides b and the magnitude of a is greater than the magnitude of b, then b must be equal to 0 because otherwise it's just impossible. And clearly the magnitude of x plus 5 cannot be 0 because a is positive and is greater than 2 in fact, and at least 2. Therefore, we must have 4x minus 1 is at most x plus 5. Then x is less than or equal to 2, and this gives the possibilities of a equals 2 or a equals 4. For a equals 2x plus 1, we have 4x plus 1 divides 4x squared plus 8x plus. Okay, one simplification we can make to avoid these annoying computations is that we can also use the fact that 2a minus 1 divides 2a minus 1, which is obvious immediately. And this gives that 2a minus 1 also divides a squared plus 5. And now we have 4x plus 1 divides 4x squared plus 4x plus 6. And we also have 4x plus 1 divides 4x squared plus x. So 4x plus 1 divides 3x plus 6. And from here, we have that We can again continue that if they divide each other, we must have 3x plus 6 is, I think I messed up somewhere. Okay, yeah, so this condition is a bit annoying to deal with. And from here, we have x is at least, sorry, there should be a less than or equal to sign. And then we have x is at least 5. We can check x equals 1 gives a equals 1, which is impossible by our conditions. X equals 2 gives 3 divides 9. X equals 3 gives 5 divides 14, which is not true. X equals 4 gives 7 divides 21, which is true. And x equals 5 gives 9 divides 30, which is not true. And then the only solutions are for x equals 2 and x equals 3. So then we can combine all the values we had so far and actually compute the values of k we get from this. And those become k equals 4 or 7 for the answer of 11, because we were asked to sum all possible k. Are there any questions?
Okay, for the last problem, we'll be going over number 8 on the SMT team round. So for this question, it's another geometry question. We are given a triangle with 3 x circles and the product of the radii of the x circles. And then we are asked to find the area of the triangle. So first, you need to know what an x circle is. So if we have any triangle like this, then we can define the ax circle as the circle that is tangent. So if we have A, B, and C, then the ax circle is the one that's tangent to BC, the extension of AB, and the extension of AC. So something that looks like this. That's a bad circle, but yeah, something that looks like this. And then and RA would just be this. So the key realization for this problem is that we can write the radius of the x circle as the area of the triangle ABC as divided by a semi-perimeter minus the length of the side it's facing, which we can call A. And we can see this by looking at the areas. So if we call this point D and this point E, we know that this E, let's call this EA, we know that EAD is equal to DB. And then we know that BD is equal to the point here. And then we know that this is equal to this. And so if we consider the area of triangle ABC, it's actually equal to the area of triangle. Sorry. Yeah, it's equal to the area of triangle AE times EA, so this area, plus the area of AE, and then EA. And then we subtract the area of BD, EA, and E, and subtract this area as well. And this is in fact just 1/2 times. So area of ABC is equal to area of EA plus area of E, so it should be AD. Why not? Yeah. Well, we'll call this point F, sorry. So AF and this is AEA, and this is AFEA. And then we subtract the area of these two trapezoids over here. And then this BDEAE and area of CDEA F. And this is equal to 1/2 times RA times AB plus BE and a bunch of other lengths. And this can be verified later. I just won't go over here. But once we have that the radius of an X circle is equal to the area of a triangle divided by the semi-perimeter minus the length of the side it's facing, we know that RA times RB times RC is equal to the area of the triangle cubed divided by S minus A, S minus B, and S minus C. And this looks suspiciously similar to Heron's formula. So if we multiply both the top and the bottom by the semi-perimeter, then S times ABC cubed. ABC cubed is equal to ABC divided by ABC squared is equal to 384, which is this. So if we cancel this out, then we have that 384 is equal to 32 times the area of ABC. And so our answer is 24. Are there any questions?